right, in section 14.2, we're going to evaluate limits, but we're not going to use a table or the graph. We're going to use some algebra techniques. So I have a list here of 5 plus 1 rule that we're going to use to evaluate the limits. So the first rule we're going to look at is when we evaluate the limit as x approaches a of a constant. All right, so some number c. So c could be positive, it could be negative, but what is the limit of a constant? Right? I am going to look at the graph to show you what this answer is. What's the function, a constant function, look like? Right? So if we had f of x equals a constant, right? What would that look like? It would look like a horizontal line at c. Right? A constant function, because it has to pass the vertical line test, right? So a constant function is a horizontal line. So no matter where we pick a, the function values is going to always be up at c, right? So since this line is at c all the time, the limit is going to be c, right? So the limit of a constant is the constant. It doesn't matter where x is, okay? The second rule we're going to look at is the limit as x approaches a of x. And again, I'm going to look at the graph to demonstrate what this limit is. So our function is x. So what does that look like? If f of x equals x, what would that look like? Well, it's a line, right? As a slope of 1, a y-intercept is 0. So it's just that diagonal line that cuts through your axis. Okay? So these function values are changing. But if I were to look at a here, then what's the function value going to be? Right? If I were to do a table of values here, this is like y equals x. So if x is 1, y is 1. If x is 2, y is 2. If x is negative 3, y is negative 3, right? So no matter where the a value is, when we plug it into this function, we're going to get that a value back out. So the limit as x approaches a of x is a, right? It depends on where we're looking. So on a constant, it doesn't matter where we're looking, the function value is always at c. But on x, if a is positive, right, we're up here, and if a is negative, we're down here, and we're at the actual a value. Okay. So the next three are going to be kind of intuitive, but it just explains how limits work. So if we were to take the limit of a sum, right? So the sum of f and g. So the limit of the sum of f and g, the way limits behave, we can take the limit of the first function plus the limit of the second function. So we can separate that sum out when necessary and evaluate it as two different limits. Right? So I say the limit of a sum is a sum of the limits. Right. So the same thing is going to occur with subtraction. So actually, let me just put a minus here. So it doesn't matter if it's plus or minus. Okay, you can separate them out. So then number 4 here, the limit of a product is a product of the limits. So if we had f of x times g of x, we could split that up and do the limit of f times the limit of g. Number 5 is the quotient one, right? A limit of a quotient is the quotient of the limits. So we get the limit of f divided by g means we can take the limit of f and divide it by the limit of g. All right, now on all of these, we're assuming that the limits of f and g exist. All right, so if the limit of f did not exist, we would not have separated it out. We would have stopped evaluating the limit at that point. Okay, and then the limit of the quotient is particular because we got to make sure we're not dividing by 0. So if the limit of g is 0, we would not split this apart. Okay, we would just do something else at this point, right? So this is only if the limit as x approaches a of g of x does not equal 0, right? And a lot of times, the limit of the denominator is going to be 0. So I want you to know we're not going to split it up in those cases. We're not going to automatically assume that this limit does not exist. There's other ways of evaluating limits when the bottom piece goes to 0, right? So the main point here, okay, when we algebraically evaluate limits is asking ourselves whether a is in the domain of the function, okay? So if a is in the domain, if the value we're evaluating the limit at is in the domain of f, then the limit as x approaches a of our function is f of a, right? So if a is in the domain, we're going to evaluate the limit just by plugging it in, okay? Now, we're still technically supposed to not let x equal a, and it looks like we're letting x equal a. But if a is in the domain, when we get close to a on the right and when we get close to a on the left, those function values are going to approach f of a regardless. So if a is in the domain, this is us evaluating the limit of a function that doesn't have a hole, right? It's a function that's a nice smooth curve, and so if a is in the domain, right, we get this nice smooth curve here. So it doesn't matter if we're approaching just on the right and on the left. Those function values are going to be approaching that point there regardless, right? So this is what our goal is to find a function that a is in the domain of, all right? So I have 7 examples here, and then I have another graphical worksheet that I would like to work through with you. So algebraically, we're going to evaluate some limits. All right, so let's look at this one first. All right, so we could treat this as 2 different functions, or we could treat it as one function as a whole, all right, and just do the limit of the whole piece, or we could just do the limit of each term with an x in it. I tend to take it as a whole function here. So we want to ask ourselves, is -1 in the domain of this function? Right, this function is quadratic. It's a parabola, right? Parabolas are defined everywhere. And so any number we evaluate the limit at is going to be in the domain of this function. So if I wanted to evaluate this limit, I can just plug -1 into the function. So I'm going to get 3 times -1 squared minus 5 times -1, right? So if a is in the domain, you just plug it in, okay? So we're going to get a limit value here of 3 plus 5, which is 8, okay? Let's do another one on this page. It's a short one. All right, so what's the limit as x approaches 1 of 5? Notice that there's nowhere to plug x in, right? So this is the limit of a constant. So this function is a horizontal line at 5. So no matter where we evaluate the limit at, we're just going to get the constant back out. So the limit of a constant is the constant, right? It doesn't matter the a value. All right, let's do another one. All right, so the limit as x approaches 0 of x squared minus 4 divided by x squared plus 4. So we always want to ask ourselves, is 0 in the domain of this function? Right? So it's in the domain if it doesn't make you divide by 0 or take the square root of a negative or cause the argument of a log to be something other than a positive number, right? There's lots of functions that we have to find the domains on. So if I plug 0 in for x, will I be dividing by 0? No, I will not, okay? So I can evaluate this limit just by plugging 0 in for x. So I'm going to get 0 squared minus 4 divided by 0 squared plus 4. And so negative 4 divided by positive 4 is negative 1. So we can evaluate this limit just by plugging 0 in. Right? Let's look at this one. All right, so the limit as x approaches negative 3 of x squared plus x minus 6 divided by x squared plus 2x minus 3. So can we evaluate this limit just by plugging negative 3 in? And really the denominator is all that matters. The domain sits here in the denominator. So what if I plug negative 3 in for x into the denominator? 9 minus 6 is 3. 3 minus 3 is 0. Okay, that's oops. All right. So if I just plug negative 3 in, I'm going to be dividing by 0, and we can't do that. But we're also not just going to assume that this limit does not exist. Right? There's algebraic techniques out there to evaluate this limit. So what we're going to do is we're going to write this as an equivalent function. So what we can do, what we can do in this problem is we can factor it, all right? So the top factors and the bottom factors. Now, because I have not evaluated the limit, I'm just changing the way the function looks, I still need to write the limit as x approaches negative 3 to indicate we are evaluating the limit of this function, right? But I am going to factor the top and the bottom. So the top is going to factor to x plus 3, x minus 2. The bottom is going to factor to x plus 3, x minus 1, right? So you notice that x plus 3 is a common factor, so we can cross this out. And this x plus 3 factor is the reason why we can't plug negative 3 in there. This is the reason for our whole, right? So remember when we studied rational functions, and if we factored it and the factor canceled, we had a whole, not an asymptote. Well, that's exactly what we're doing here, is we're finding where this function has a whole, and we're canceling it out. So I'm going to cancel the x plus 3 factor, right? So now, can I evaluate the limit? Now, can I plug negative 3 into this function, right? Yes, because negative 3 is in the domain of this new function, right? Now we're not going to get 0 in the denominator like we did before. So because we're evaluating the limit, we're actually plugging negative 3 into the function. I don't need to write the limit anymore. I can just write the value that we're going to get. So we're going to get negative 3 minus 2 on top. We're going to get negative 3 minus 1 on the bottom. And so negative 5 divided by negative 4 is a positive 5/4. Okay. So what I'd like to do, just quickly, because it's pretty interesting, right, is I'd like to graph this function and this function on the same graph and show you what's occurring here. So I'm going to type in the original function. And then I'm going to type in the function after we reduced it. So the factored and reduced form. Right. So we're saying that this limit of this function equals the limit of this function, right? And it's not because they're equal at negative 3, right? Because the function here at negative 3 does not exist. The function here at negative 3 is 5/4, right? So they're not exactly equal. But what I want to do is I want to show you what happens when you graph this function. So the top one is going to graph in blue, and the bottom one's going to graph in red. So the blue one is going to graph first. Ooh, I should have changed my window, but maybe this is going to be okay. So here's the blue function here and here. Oh, except for I'm looking at negative 3. So, okay, let me change my window. Negative 10 to 10. Negative 10 to 10. Okay, let's graph it again. So here's the blue graph. Okay, with an asymptote at 1. And then here's the red graph, completely covering up the blue graph, right? Absolutely everywhere. They are equal, right? So, but I want to show you that they're not equal at negative 3. So I'm going to calculate the value. So calc value. I'm going to plug negative 3 in there. So right now it's on the blue function. And if you notice, it doesn't give you a y value. That's because there's a hole in the graph. Now if I use the scroll arrows to change it to the red function, you notice now that it puts a cursor on the graph. And at negative 3, the value of the function is 5/4, right? So the blue one doesn't have a function value. The red one does. But if you look at the lines, right, the lines are exactly the same. So the limit at every single point between the blue graph and the red graph is going to be the same. At negative 3, the blue graph has a hole, right? But the limit is still the same as the limit of the red graph that doesn't have a hole, right? So I think it's really pretty interesting when you look at the graphs of these equivalent algebraic expressions. All right, so let's do another one. Okay, so can we first off evaluate this limit just by plugging 1 in? Okay. What happens when you plug 1 in? Particularly, what happens in the denominator? So if we plug 1 in, 1 plus 3 is 4, 4 minus 4 is 0. Right? So we would get some number on top probably and 0 on the bottom. Right? And you know you can't divide by 0. But we're not going to write does not exist here. We're actually going to try and find an equivalent fraction that doesn't have division by 0. And the way we can do that is to factor. All right? So the top has 4 terms. So in order to factor this, I'm going to have to do grouping. The bottom we can factor pretty easily. But I'm just going to do some scratch work down here and factor this without having to write the limit at each step. Okay, so I like to keep my limit nice and clean, right? And if I have to do a lot of algebraic work, I'm going to do it outside of the problem here. So x cubed minus x squared plus 3x minus 3. Let's go ahead and group, right? Group the first 2 and the last 2. So I can factor an x squared out of the first group. We're left with x minus 1. We can factor a positive 3 out of the second group. We're left with x minus 1, which is good. So this factors to x minus 1 times x squared plus 3. Okay. Now the bottom here is going to factor, I don't need to do scratch work there because I can factor that without multiple steps here. So we have not plugged 1 into this function. We're just changing this function to an equivalent form. So it is important that I indicate we still need to evaluate this limit, right? It's not until you actually plug those numbers in that you can stop writing the limit. So the top factor is to x minus 1 times x squared plus 3. The bottom is going to factor to x plus 4, x minus 1, right? Multiply to negative 4, add to positive 3. So it does look like we have an x minus 1 factor. And this is what was causing the problems, right? If we were to plug 1 in the top, we'd get 0. And plug 1 in the bottom, we'd get 0. And that's because we have this x minus 1 factor. So if I cancel that out, it's canceling that whole, right? If we have a common factor in the top and the bottom, there's a hole at 1. If I cancel that hole out, then the resulting function doesn't have a hole in it anymore. So can I plug 1 in at this point? Absolutely. So since I can plug 1 into this function, I'm evaluating the limit, and I don't need to write that anymore. So I'm going to plug 1 in, 1 squared plus 3 over 1 plus 4, and that's going to give us 4/5, right? So algebraically, you're going to factor if possible, right? There's other algebraic techniques that you'll learn in the actual calculus course, but for now we're just going to kind of focus on factoring. All right, so let's look at this example. Right, the limit as x approaches 1 of x cubed minus 1 over x minus 1. So if you were to plug 1 in, you would get 0 over 0, right? Anytime you get 0 over 0, the answer is not, it doesn't exist, but there's more work to be done, okay? So I don't know if you remember how to factor cubics, okay? Lots of people don't. But what I do want to show you here is that synthetic division works really well, right? Because we have x cubed minus 1 being divided by x minus 1. So I can do this division. We can use long division or we can use synthetic, but most of the time people opt for synthetic division. So I'm going to do some scratch work to actually divide this out. Okay. So the factor is x minus 1, so we're going to divide by 1, right? That's the 0. And then when I list these coefficients out, I want to make sure I'm putting placeholders for all those missing terms. So the coefficient of x cubed is 1, x squared is 0, x is 0, and the constant is negative 1. Okay. So add down first. 1 times 1 is 1, add down. 1 times 1 is 1, add down. 1 times 1 is 1, add down, 0. So you notice we got a 0 remainder, and so it evenly divides. So the other thing is this is 1 degree less. So 1 is the x squared coefficient, x coefficient, constant, and remainder. So at this point I have it factored, right? I have x minus 1 as a factor, and I also have x squared plus x plus c as a factor, right? When you do that synthetic division, you find that quotient. It really is factoring your polynomial, right? So I'm going to go ahead and write the factored form of the cubic. All right, so the cubic factors to x minus 1 times x squared plus x. Oops, I wrote constant here. I meant 1. Okay, x plus 1. I had constant on the brain or something. All right, so now that I have it factored, then I can cancel the x minus 1 factor. And that's the reason for the hole, right? When you have common factors on the top and the bottom, you have a hole. So now all that's left is x squared plus x plus 1. Can I evaluate the limit by plugging 1 in? Absolutely. So I'm going to get 1 squared plus 1, which is 3. Okay, so if we evaluate this limit, we will get an answer of 3. But pretty slick, right? Using that synthetic division to factor a cubic. Okay, it's a really nice trick. All right, one more. It's a short one, so I'm going to fit it right here. Okay, the limit of x. Right, the limit as x approaches 4 of x. So can we plug 4 into this function? Absolutely, right? And if I plug 4 in, I'm going to get a limit value of 4. So remember that rule we went over? The limit as x approaches a of x is always going to be a, right? So it's just us plugging 4 in to that function and simply getting 4 as a result, right? So try those algebraic techniques out, right? I have one more thing I'd like to show you, and that's we're going to kind of work all of these limits out, okay? But first, I'd like to go ahead and define for you a right hand and a left hand limit, because we do have what's called one-sided limits. So at the bottom of this page here, let's go ahead and define those. So one-sided limits, meaning we're looking at the limit as x approaches a on one side only. The original limit definition, I call it, is a two-sided limit, right? We're looking at the right and the left, making sure they agree. On a one-sided limit, we're just looking at one side, okay? So we have what's called a left-hand limit. And on a left-hand limit, we're only looking at the left-hand side, right? So the left-hand limit is going to look like this. The limit as x approaches a on the negative side. All right? So a on the negative side. So we put a negative sign in the exponent, right? So that just means we're going to pick a values strictly less than a. All right? So choose a values strictly less than a. Oops, sorry. So the word strictly here is important because in a limit we can't let a equal a. So this is not a less than or equal to. This is strictly less than a. Okay, not greater than, not equal, only less than. We're only going to pick a values less than a when we evaluate a left-hand limit, right? So similarly, we have a right-hand limit. And so the right-hand limit, we're going to pick x values on the positive side of a, right? Greater than a. And so this can equal some limit L, right? So on the right-hand limit, we're going to choose a values strictly greater than a. Right? Not less than, not equal to, only greater than a. So I think it is important to note, right, that when we were evaluating the limits before, and the limit didn't indicate a side, right? I call this an overall limit, right? There is no plus or minus here on the a. So this limit only exists when the left-hand limit equals the right-hand limit. So we kind of were doing one-sided limits because you can only look at one side at a time, right? So now we just have a name for it. Left-hand limit is on the less than side. The right-hand limit is on the greater than side. And the overall limit only exists if the left-hand limit equals the right-hand limit, right? So let's go ahead and look at this graph I have at the top of the page. And let's go ahead and answer each of these questions. Right? So the first question, if you can't read it, is x approaching -6 on the negative side. Right? So let me go ahead and write that up here. 19. The limit as x approaches -6 on the negative side. Right? So we're going to pick, and we're going to look at only the left-hand side of -6. Right? So -6 on the left, less than 6, we're looking at this function here. Okay? So this function here, as we get closer to -6 but less than 6, it's going off to infinity. And so I'm going to write does not exist here. Okay? Because the limit does not exist. Or we could write infinity is also acceptable in most cases, but technically the limit does not exist. Right? Number 20 is the limit as x approaches -6 on the right. Okay? -6 on the positive side. So if I were to pick values greater than -6, now I'm on the right-hand side of -6. Not too far away, okay, not all the way over here, close by, right? And so close by, these function values are approaching -infinity. So again, I would do does not exist or -infinity. Right? All right, number 21. Find the limit as x approaches -4 on the negative side. Okay, so on the negative side of -4, we're on the left. So here's -4. On the left of -4, we're looking at this piece here. Okay, but instead of heading farther away from -4, I need to head closer to -4, right? So as we get closer and closer to -4, these function values are going up to 2. Okay, so remember, it doesn't matter what it's doing at -4, just what it's doing close by. So the left-hand limit here is approaching 2. Okay, so we're going to put 2 here. I'm just going to write it down here. Now what about -4 on the positive side? Okay, if I just focus on the right-hand side here of -4, we don't care what the function is doing over here. Now we're on this piece. And the closer the x values get to -4, those function values are decreasing to -2. Now this one has a hole, but holes don't matter when evaluating the limit. Okay, so we have a left-hand limit equaling 2 and a right-hand limit equaling -2. So what do we know about the limit as x approaches -4? Right? We haven't indicated a side, so this is from both sides. So since the left-hand limit is going to +2 and the right-hand limit is going to -2, we say this overall limit does not exist because the left-hand and the right-hand side have to equal and agree in order for the overall limit to exist. All right? Now, what's the limit as x approaches 2 on the negative side? Right? On the negative, that's less than 2. Right? That's here. So less than 2, we're looking at this little piece here. And the closer we get to 2, this piece looks like it's approaching, I'm going to assume 1. Okay? And the limit as x approaches 2 on the positive side. On the positive side, we're picking values greater than 2. Right? Don't go too far away. Stay close to 2, but on the positive side. So those function values are decreasing, and they're going to decrease and approach -4. Right? It's never going to equal -4, but it is going to get awfully close. Okay? So again, the left-hand limit and the right-hand limit do not agree. So we can say that the limit as x approaches 2, okay, the overall limit does not exist. Right? Does not exist. So I think I answered number 25 already. Does the limit as x approaches 4 exist? Oh, no, we didn't. Okay. Does it exist? Does the limit as x approaches 4 of the function exist? Okay, 4 is here. So this isn't one-sided, right? This is both sides. So on the right-hand side, it seems like it's decreasing to 0. On the left-hand side, it's increasing to 0. So since they're approaching the same value, 0, this limit does indeed exist, and we would say this limit is 0. Right? What about the limit as x approaches 0? Okay. X approaching 0 is here. What is the function doing there? Okay. On the right-hand side, it's increasing to 3. On the left-hand side, it's increasing to 3. So this limit exists as well, right? And it equals 3. So there were multiple places on this graph where the limit did not exist, right? It didn't exist at -2. It didn't exist at -4. It didn't exist at 2. But it did exist everywhere else, right? One-sided limits tend to always exist unless it's going to infinity, okay? What's interesting here, let me just talk about it. Okay, I know I'm at 36 minutes, but I want to talk about the limit as x approaches 6 of this function. Now, I haven't indicated a side here, so there's 2 sides here. And if you look at this graph, we only know what it's doing less than 6. We have no idea what this graph is doing greater than 6. So because this graph doesn't have anything on the right-hand side, let me write limit of a function here, we would say this limit does not exist, okay? Because we have no, maybe it's not defined over there whatsoever, and if a function is not defined, then it can't exist, right? But we do know what the limit as x approaches 6 on the left-hand side is, right? 6, but less than 6. And less than 6, we know that that limit is indeed 2. It's the right-hand limit that we have no idea of how to calculate. So if the right-hand limit doesn't exist, the overall limit cannot exist. All right, so I hope that helps you evaluating limits in this class and in the future calculus classes to come.